Welcome everyone, I'm Matteo Bernetti and I'm a PhD student at the University of Twente in the Netherlands. I'm very excited to be here, not just because this is the Winter Simulation Conference, but also because this is my first conference ever, as I started my PhD in February. My project is about simulation of logistic processes, and today I will show you our general simulation framework for smart yards. So we will first go through an introduction, then the concept of smart yards, general simulation framework, some models and results, and finally further research. So let's start by challenges that logistics sector usually faces. Usually cost reductions, quicker deliveries, think about same-day delivery by Amazon. And then also problems with flexibility and reliability of supply chains and these very quick deliveries. Then there are problems with safety, car accidents, for example, or accidents on highways, and sustainability issues. Think about the European goal of reaching zero emission logistics by 2050. So logistics companies and authorities, port authorities, for example, are looking at new concepts to solve this and tackle these challenges. For example, they're looking at connected and automated transport. But what is connected and automated transport? We define connected and automated transport, CAT, as transportation solutions for passengers or freight utilizing increasing degrees of automation and connectivity. The European Commission also wrote a report about CAT, and they define automated as vehicles having safety critical functions and operating without direct driver input. And the connected part, well, they define it as exchanging information wirelessly. Typical examples of this can be automated guided vehicles, which are usually used in container terminals and for the movement of freight. But also there are new vehicles like the Volvo Vera, which is an automated vehicle, almost autonomous actually, which can drive on public roads next to other private vehicles, traditional vehicles, normal cars, for example. And for connection, we can think about cloud networks, but also very popular now, Internet of Things, which connects all elements in a network. So, to put logistics and CAD together, we decided to focus on hubs. Hubs are the nodes of the logistic networks, and they can be container terminals, distribution centers, or even airports. So we developed this concept of smart yards, which is any logistic area with specific features. These features are logistics centers, so companies over there, terminals, warehouses, a decoupling area or central gate where incoming modalities trucks stop, park, decouple the trailer and give it to automated vehicles that bring it to logistics centers. Then we also have a rest area for drivers next to the central gate where drivers can rest or sleep, eat, or repair their containers, any services that they might need. Then we have transport modalities coming to the smart yard, can be trucks, but also barges, planes, trains, even drones. And then we have an automated vehicle system handling the internal movement of freight at the smart yard. And next to these physical elements that I explained to you, which compose this physical smart yard, we'll also have a digital smart yard. And that is a cloud-based network, for example. It's connecting all of the elements, exchanging information, but also connecting the smart yard to other smart yard or hubs in the world. Now, what is the main problem of this concept? Think about it for a second. Well, if you were thinking about it being very disruptive, you are right. What do I mean? I mean that if you try to implement this system with automated vehicles and a parking area, well, it's very expensive, but also you don't know the effects of this. What are the results? Are we sure it's going to be better? And maybe we create a lot of problems for the flow of freight, and it is not what port areas or any hub might want. So as a solution to that, of course, we're going to use simulation. Well, this is the Winter Simulation Conference after all. In our simulation, we use both discrete event simulation and agent-based simulation. This allows our framework to reach two goals: flexibility and reusability, and to model AGV behavior. The first one is important to us because we want to model all kind of hubs, logistics hubs, um, so flexibility, and to make it easier and faster reusability. And agent-based simulation instead allow us to represent the complexity of the AGV behavior in the system. Now, we followed the conceptual modeling framework from Robinson. Therefore, we have inputs, assumptions, key performance indicators, flowcharts, and logic agents. Now, instead of going into the details, I will use the example of the Portable dike and hint to inputs and key performance indicators to make it easy. Focusing on this logistics center, it's a terminal, it's a combined cargo terminal. We see that it is serviced by barges, trains, and trucks. So this is already a type of input, which modalities get there. But maybe also the number of cranes and the speed of this crane in unloading and loading modalities. And if we think about key performance indicators, well, it could be the queues at these cranes. How long are these queues, and do they change when we improve the internal flow of freight at this smart yard, at this port area? Does it get better because there's less congestion, maybe? Moving on to the agent-based simulation part, we adapted the multi-agent system from Gerrit to tackle two main challenges: traffic complexity, think about traffic in a port area, and multiple stakeholders. So the idea that multiple independent companies are using the same shared AGV fleet. Our multi-agent system is composed of three main parts: logistics center control, vehicle control, and smart yard control. The smart yard control is a centralized system shared by all smart yard, which through the routing agent computes the best routes for the AGVs to reach their destination using the input of the location manager, which has data on the infrastructure. The AGV tells the central dispatching agent its position and deals with conflict handling, as well as telling the battery manager about its battery so that it can go back to recharge. And the logistic centers deal with scheduling operation and sending tasks, requests for transportation tasks to the central dispatching agent. Of course, the logistics center control and vehicle control are instantiated for each logistics center and vehicle. Going back to our challenges, we dealt with traffic complexity by moving the conflict handling at the AGV level, so performing that in a decentralized way. This lowers the burden on the central system and is just done by AGVs engaging with each other when they are in a conflict. Also, AGVs can bring awareness to the location manager on the congestion status of the infrastructure through their sensors. And regarding multiple stakeholders, we split the dispatching agent at the logistics center and at the central smart yard control part in two, because we want the LC dispatching agent to represent the interests of each logistics center, but also to send the information in a more disclosable way and send it to a central system, which then doesn't share it with other companies, and this helps in keeping sensitive information safe. Moreover, the central dispatching agent can enforce some specific policies, for example, fare allocation mechanism, such that the AGVs are not solely sent to big companies which have a bigger impact on the flow of freight in this market, but also to smaller companies such that they don't feel neglected and don't drop out of the system. So this was our multi-agent system, and now we move to the model. Finally, we get to the model. In our study, we created a first model, not including all of the simulation framework, but just it's a first step. And here we represent a small part of the Amsterdam Airport Schiphol in the Netherlands, where we only have export trucks coming in and delivering freight at the logistics centers. And also we have some simple congestion effect by keeping track of the number of vehicles on the road and at the logistics centers buffer area, so outside of them. And based on that, we reduce the speed of all the vehicles in the system by a certain percentage. We also have 4 scenarios in this that we can reproduce in this model. And the first scenario is pretty easy. It's just the arrival of trucks and then moving directly to the logistics centers, as you can see here. Now, the other scenarios have a calling system. So basically, trucks go to the truck parking area, and when they're called, they move to the logistics center. Otherwise, for scenario 3 and 4, we first have trucks going to the decoupling point, and then in scenario 3, other traditional vehicles, yard tractors, for example, move the freight to the logistics center. Otherwise, we have automated vehicles moving freight to the logistics centers. Using the model, we experimented and got some first insights on the truck parking area, decoupling, and AGVs. So we performed 4 experiments, which correspond to the 4 scenarios, and I would like you to focus on the average travel time and the average congestion of the buffers of the logistics center. So if we look at experiment 2, where we use truck parking, we see that the average travel time decreases quite a lot and the congestion also decreases. Therefore, road safety probably increases. Then if we move to experiment 3, where we decouple using traditional yard tractors, we see that actually average travel time and congestion increase from the truck parking scenario. So not very nice. And going to the 4th experiment with AGVs, we see that the average travel time increases again while the congestion remains the same. Why is this increase? Well, because the AGVs in our model are assumed to move slower than other vehicles, traditional vehicles, because of safety reasons. So what can we understand from this? Our takeaway for small areas only is that truck parking reduces congestion and increases safety. However, AGVs, decoupling, and the fact that we pull resources together doesn't really have any proper benefit for small areas. That is probably because for AGVs to have some effect with their, for example, smarter routing or awareness on congestion, you would want to have a more complex system like a port area. We showed you a small-scale model which partially implements our simulation framework. Therefore, before moving forward, I'm very happy to show you what a full-scale model would look like. And in this model, we imported information on the network and infrastructure at the port area using OpenStreetMap. So welcome to the Port of Moerdijk. As you can see on the right, we have the decoupling point and the truck parking area, and then we have the roadways, railways, and waterways. This can be used by modalities to reach their destinations, which are automatically routed using the pre-made function in the software. Here you see that the barge will start unloading its containers one by one, and after a while that it is unloading, it leaves, of course, and then trucks start coming in using also the roadways automatically created, and they also keep a distance between each other using some very simple coding now. So this kind of represents congestion. Now, finally, we can move towards the end of this presentation. Very briefly, this is what we would like to do in the future. So first, we will model more cases to assess flexibility of the simulation framework and develop an accurate AGV system through which we can also evaluate different dispatching algorithms, routing algorithms. And in the future, in the long run, we will of course evaluate the smarter concept for different types of hubs, of port areas, for example, and maybe test different CAT concepts, maybe platooning at the decoupling point, or how to reschedule operation using advanced information from other yards. And finally, we might want to achieve a digital twin by implementing the simulation framework at these smart yard areas. Thank you very much. This is the end of my presentation. I hope you enjoyed it. We went from problems in logistics to the smart yard concept and the general simulation framework to model that. Then I showed you some models that we actually coded and some results for small areas. If you're interested in smart yards, please send me an email. Otherwise, know that my PhD project is part of a bigger project called the Catalyst project. If you would like to know more about the consortium of port areas and other partners taking part in that, and the other topics that we research, please scan the QR code. Now it's time for the Q&A session. See you there.